Well, hi guys, we're going to have a look at second derivatives today. This is very exciting, second derivatives, because it's got a marvellous practical application which we'll learn about in the next video after this one. Let's go. Notation. Well, if we consider the function y equals f of x, the first derivative with respect to x is referred to as dy dx, or y dashed, or f dashed of x. They're all equivalent representations or notations for the first derivative. The second derivative with respect to x is the derivative of the derivative. The derivative of the derivative, and no, I haven't got a speech impediment. Well, I don't think I have. And is referred to as d2y dx squared, right? d2y dx squared. And d2y dx squared is y dash dashed, or y double dashed, and that's also the same as f double dashed x, right? It all makes sense, doesn't it? Now, a practical interpretation in calculus would be the gradient of the gradient. That's what the second derivative would be, or you could say, a little bit less mind-bogglingly, the rate of change of the gradient. Okay, you get that? Good. Let's do some examples. Now, we're going to find the second derivative of each of the following with respect to x, okay? So we've got f of x equals 7x to the 4 minus 4x squared minus x to the minus 3. That's part A. And part B, we've got y equals e to the x cos of x. I smell a product rule. Do you? Sniff, sniff. Now, here's A for us today. That's going to be very easy, isn't it? Polynomial stuff. So f dashed of x would be 4 7s to 28x cubed minus 4 2s to 8x to the 1 plus 3 times x to the minus 4. That's the first derivative. Now, of course, we've got to do the second derivative now. What is it? Goodness. So what have we got there? 3, 28s are 84x squared minus 8 minus 12x to the minus 5. Okay, just be a bit careful. You don't get anything wrong. But it's just basically doing the same old thing again when you do the second derivative. Okay, let's do the next one. We've got y equals e to the x times cos x. Therefore, dy dx is going to be left d right plus right d left. Okay, now can you work that out? Can you work that out? That's d right, that's the derivative of cos x. And then you've got, that's u dv, or left d right, plus right d left. And d left is just the same as the actual function itself. E to the x has a derivative of e to the x by the product rule. So now that's it, guys, that's it. So if you were going to just fix it up a little bit, that's what it would look like, and it would be mighty fine. Oh, now we're going to do the second derivative, of course, and you would get, goodness me, what is this? So we'd get, right, let's just work that out. Yes, it makes complete sense, because this first term here is just, I've just put the minus, that's that minus there is here, then you put a bracket, then you do the derivative of e to the x sine x. So it's left d right plus right d left. Okay, that's coming from this term here, this minus e to the x sine x. Now the derivative of this, well, that's the same as what we had up here. So basically we just take that result there of the derivative of that and just do it all over again down here. Okay, that's the derivative of e to the x cos x. So now when that all comes out in the wash, basically these e to the x cos x terms actually cancel each other out, and you just get an accumulation of these e to the x sine x, two of them, and then both negative, so you get minus 2 e to the x sine x. How interesting, isn't it? Yeah, it's a bit of a mind boggle when you get this, see this second term here after the first derivative. Well, when you do the derivative of that, that's basically what the original function was anyway. So basically the derivative of that is going to be that, if you know what I mean. Yes, so it's got a bit of a Sudoku there, or some kind of a mind buster. Alright, so let's go. Some more examples for you today. Find the rate of change of the gradient. Now that's second derivative. Come on, you know that means second derivative. The rate of change of the gradient of y equals sine x when x is pi. Hi, pi, and we'll go for it. So we've got y equals sine x, and therefore dy dx equals cos x. That's the gradient function for sine x. Now we know that the gradient of that, which was, now have a look, dy d by dx of dy dx, or d2y dx squared, is just going to be minus sine x. That's the derivative of cos x, is minus sine x. That's the rate of change of the gradient of sine x. It is. Now, we're going to put x as pi in there. And what do we get? What's sine pi, guys? Nothing. It's nothing. It's nothing. So there we go. That's what it is. There's your answer. So when x is pi, the rate of change of the gradient is 0. Okay? What's this one? If y equals sine 2x, find the value of dy dx squared plus a quarter of d2y dx squared, and show that this result is independent of x. Well, that's going to be easy. We just have to work out the first and the second derivative, plug and play into this equation, and the answer will be ours. So we've got y equals sine 2x. What's that? dy dx equals 2 cos 2x by the chain rule. Yes, the chain rule. Note the 2 out the front here. Right? So it's sine of blob. The answer is going to be cos of blob times d blob dx, and where blob is 2x, or if you like, u. Okay, derivative of u derivative of 2x with respect to x is just 2, isn't it? Now let's go for the second derivative now. Okay, so what do you think it would be, guys, before I reveal it to you? I predict it'll be minus 4 sine 2x. Would you? Oh, yes, it is. Would you? Did you agree? Did you agree? If not, you better go back and learn your chain rule, okay? Put the training wheels back on and do your chain rule from scratch again, and you will get it, okay? So now we've got to plug and play now and put this into the equation. So therefore, y dashed, using that notation, squared, plus a quarter of y double dashed, squared, wait a minute, comes to this, right? Okay, so there's y dashed squared and y double dashed squared and a quarter of it. So what does that come to, guys? Well, hopefully this is going to come out to be independent of x, so let's work it out. Oh, look. I know what to do. Do you? Do you? What's cos squared plus sine squared? Therefore, what's 4 times that? Are you getting it? Is the penny dropping? Clunk. There you go. Look, it's 4. And that's definitely independent of x, isn't it? You see, it all works out in the end, yes? Like a gigantic, wonderful fairy tale, yes? And maths is just a great big fun game. So let's see what else we've got in store here. Oh, with CAS. Okay, let's have a look at the CAS. So what have we done here? We've said sine 2x is made to be f1 of x, okay, assigning that to f1 of x. Then we've done the derivative of that, and we've stored that to f2 of x, okay, d by dx of f1 of x, storing that to f2 of x, and you get it done. And then you do, what have I done there? Okay, so therefore the second derivative, look at that notation, see? The second derivative, that's easy to do on the calculator. Second derivative of f1 of x, we're going to put to f3 of x, and we get it done from the calculator, don't we? And then we're just going to do, this is the thing we had to plug it all into, and hopefully it came out to be independent of x. That's the first derivative squared plus quarter of the second derivative squared. And wouldn't you know it, we get 4. Isn't that mighty fine? So it's good, isn't it? Yeah, it's great. There it goes. So that's the end of our little video on second derivatives. Look, they're very straightforward. You just got to take the derivative twice, and just remember your product rule, your quotient rule, and your chain rule, and everything will be sweet. All right. So thanks for that. The next exciting video is going to be on points of inflection. So that's going to be an absolute blockbuster. So look forward to that, and we'll see you in that video. Bye for now.